we will continue on the solid liquid separation. Before you send the slurry to the filtration process, sometimes you may have to carry out something called pre-treatment. That means you need to pre-treat the slurry and then send it to the filtration process. So there are different types of pre-treatment strategies adopted. This pre-treatment strategy improves the filterability of the broth, because if you recall, after the fermentation the broth may be highly viscous, the broth will contain several types of particles, sticky particles, sand like particles, precipitated salts, dead biomass, metabolites. So you need to improve the filterability, otherwise the whole material may spoil the filtration unit as well as it will slow down the filtration process. So a few of the important techniques which are adopted for improving the filterability includes heating. That means you heat the material which you are going to filter, you adopt something called coagulation and flocculation, or use something called filter aids. These filter aids improve the flow of the liquid through the filtration unit, either by improving the porosity of the bed or doing adsorption of some of the unwanted solids which hinders the filtration process. We will look at each one of these techniques slightly in more detail. Heating, this is a very simple method. You slightly heat the material or the liquid which you want to filter, so that it increases the flow. That means it reduces the viscosity of the medium, and it also increases the handling of this particular liquid. But it is not very suitable if you have metabolites or if you have proteins which are thermally labile. That means the protein may lose its activity because of your heating, or you may have some metabolites which get denatured or deactivated because of your heating. And sometimes when you heat, you may also lead to certain chemical reactions, unfavorable chemical reactions. So you need to be sure that such things do not happen when you heat your material. Actually, one advantage of heating is also it is pasteurizing your broth. That means if there are some viruses or if there are any organisms which are pathogenic, it may kill them, especially if you want to pasteurize milk. Heating is a very good technique. If you want to pasteurize any food products, heating is a good technique because it kills these viruses or pathogenic organisms. But the most important point you need to keep in mind is whether the protein or metabolites present which you would like to recover are thermally unstable. Then in that situation you will not be adopting heating like a technique. Heating you can do in a batch operation, or you can also do in a continuous operation. In a batch means you take the material, the broth, in a large vessel and heat it and then cool it down and then send it to filtration, or you may do it in a continuous tubular type of arrangement. Suppose I want to process a polysaccharide like a pullalan, which is fermented from a microorganism. So when we heat it, what happens is there are certain precipitates that happens, precipitates of the protein without affecting the pullalan. So the proteins which may be hindering the recovery of pullalan can be removed by this type of heating. So when you heat, the proteins get denatured, and when the proteins get denatured they precipitate out. So you can separately recover the pullalan. So that is the main advantage of in this particular case heating, and it is a very good separation process. Generally you heat it up to 80 degrees centigrade for about 20 minutes. So you see that when I heat at 80 degrees centigrade, most of the proteins are becoming deactivated at that particular temperature. So whatever proteins present, once they get deactivated, the chances are they will precipitate out actually. So if you have a situation where you have an organic molecule and you have some unwanted proteins where you are more interested in the organic molecule, then heating is very good. But if you are interested in the protein part of it, then you are in trouble, because you cannot raise it to such large temperature, and most of the proteins will completely get denatured. The another approach by which you could improve the filterability is the coagulation or flocculation. We talked about this in a couple of classes back, techniques called coagulation or techniques called flotation or flocculation. So you can aggregate fine particles or cell mass. So when you aggregate these fine particles, it becomes easier for you to separate in a centrifuge. Otherwise, if they are in a non-aggregated stage, the particle size is small, plus they are having an electrostatic repulsion. So when you centrifuge, they do not get separated so efficiently. So in a coagulation or flocculation type of approach, what you are doing is you are breaking these electrostatic repulsions, number one, which leads to these material to come together and form aggregates. So in coagulation, what you do is you are forming small flocks from dispersed colloids using some coagulating agents. So the small flocks are formed from colloids that are well dispersed. So you generally use something called electrolytes. So these electrolytes affect their electrostatic charges, so they make these colloids which are far away from each other to sort of coagulate and form flocks, and these flocks, if they are heavy, they can start settling down, and because the flocks have higher particle size, even in centrifugation they can be easily separated. The other approach is the flocculation, where you are agglomerating these flocks into larger settleable particles. So you are again using something called a flocculating agent actually. So you can use polyelectrolytes, you can use salts like calcium chloride and so on. So coagulation, flocculation is generally adopted. If you look at a fermentation downstream, that will be the first step before you actually take it to a centrifuge or a large filtration setup. Even in, for example, in a fermentation towards ethanol, you call something called a clarification. That means there are a lot of fine particles which make the entire slurry very hazy. So you add some coagulating or flocculating agent, which are like electrolytes or salts, and allow some of the particles to coagulate and settle down, and then you go to the filtration setup. That could be any normal bed filter or a centrifuge. So the advantage of using a coagulation or a flocculation is to enhance or improve the filtration process. So the common flocculants that are used, and there are large number of flocculants which are used actually, and the common flocculants is what I am going to tell you, and it also depends upon the type of broth. So if suppose you have a glucose based broth, we may use some salts like polystyrene sulfate, bentonite. Bentonite is a clay, a polyacrylamide, this is a polymeric material, polyethyleneamine and so on. So this one tells you how much is the quantity of these flocculants used per 100 grams of dry cell. If it is a hydrocarbon based broth, then again you can use polystyrene sulfate or bentonite or polyacrylamide, but then you see that the polystyrene sulfate quantity changes depending upon the type of broth, and bentonite quantity changes depending upon the type of broth, and here polyacrylamide is not very effective whether it is a glucose broth or whether it is a hydrocarbon broth. So if it is a cell resuspended cells in a buffer, you see that again the quantity of polystyrene sulfate and bentonite changes, but polyacrylamide is ineffective. If it is a penicillin or an antibiotic based broth, then we can use calcium chloride, and if it is a dilute slurries, we can use electrolytes. Generally polyacrylamide is very good for water treatment plants. You know, we have a very fine suspended particles, it leads to a nice flocks by using polyacrylamide type of material. The third approach by which you can do a pre-treatment is use of filter aids. These filter aids enhance the filterability of the fermentation broth. These are materials you separately add and then you perform the filtration process. So when you do that, this material sometimes absorbs some of the impurities present in the broth, or it also improves the filterability, that means it increases the porosity of the bed. Suppose if your cake is compressible, what happens, the cake compacts on the top of the bed and hence the flow of the liquid slowly starts going down and finally there is absolutely no flows. So what do you do? By adding a filter aid we can increase the porosity, thereby preventing the compacting nature of your solids. Generally you add materials like starch powder, cellulose, inactive carbon, diatomaceous earth, rice husk, starch. So these are material which does not get compacted at pressure. Generally the concentration varies depending upon the type of solids you are trying to remove from your fermentation broth. So the quantity may change between 0.5 to 5% weight by weight. So basically what does it do? It reduces the compressibility of the biomass, it reduces the specific cake resistance. So if you remember, specific cake resistance in Darcy's law comes in and it has a very important bearing on the flow of the liquid as well as the rate of filtration. So it decreases the specific cake resistance. Generally the particle size of these filter aids are between 2 to 20 microns. So there are some disadvantages in use of filter aids. If there are advantages, there are always disadvantages, any process you select. So the disadvantages is the clarity of filtrate is less when you use large size particles. If you have antibiotics, these antibiotics may irreversibly bind to the filter aids and then you will not be able to recover the antibiotics. If that is your desired product, you are losing your product in the filter aids. For example, aminoglycosidic antibiotics, they may bind irreversibly to diatomaceous earth, so you are losing the product, so the yield goes down. So you need to also do some optimization study, how much of filter aid I need to add, what should be the particle size of the filter aid and so on actually. Number 4, it contaminates the solids. So if I am interested in the solids, then I have filter aid also mixed with the solids, then how do I then remove the filter aid from the solid? That becomes an issue. If I am interested in the liquid part of my slurry, then there is no problem, but if I am interested in the solid part, like especially in cell harvesting where I am interested in the cells not on the liquid part, then I am in real trouble because filter aids also will be there and it is very difficult or impossible to remove the filter aid from the solid cells. So you need to consider all these aspects before deciding on the type of filter aid you would like to select as well as the particle size of the filter aid. So they can be applied in different ways, these filter aids, like I can add this filter aid as a dosage to the suspension during the filtration process actually, okay. So what happens is the impurities, that is the solids that are settling down on top of my filtration aid and the filter aid settle, so they can be removed together, okay. So it is like a filtration process where I have the cake as well as the filter aid retarding the flow of the liquid. Second approach is I can use it as a pre-coat, that means initially I will just pass filter aid, so the filter aid initially settles on top of my filter cloth or filter medium and then your biomass or the solid starts settling on top of that. So the filter aid does not go and block the holes in my filter cloth or filter medium, so that is called a pre-coating. So you can do it that way, that is doing the pre-coating process. If you are doing depth filtration, so again you can use it as a pre-coat. This can be done if the concentration is low as well as the particle sizes are very small, because if the particle sizes are very large in depth filtration, the filter aid will not reach to the bottom of the filtration unit. So filter aid can be used or applied in 3 different ways. during the filtration process. So the first approach is you add it as a dosage with the slurry, so the solids in the slurry as well as the filter aid will settle on top of it, and they form a mixed bed. Because the filter aid does not get compacted, the porosity of the bed is very high, so the liquid flows nicely. The second approach is the pre-coating of the filtration unit, that means the filter aid goes and settles on top of the filter medium initially, so the solids will not go and close the pores, or whether the solids will not block the pores, thereby maintaining your flow rate. The third approach is if you are using depth filtration, again you can use the filter aid as a pre-coat, but here you need to keep in mind that the particle size of the filter aid has to be small, so that they travel right down to the bottom of the filtration unit. What are the properties of these filter aid? They have to have certain important properties. Okay, there are different types of filter aids, and they have different permeability values. They are fit for different pore size in microns. They have different values of compactability or compressibility as we call it, and they have different levels of trace metal contamination, and they can lead to silicosis. Okay. So if you are looking at compactability, cellulose has higher compactabilities, whereas perlite like material has medium compactability. If you are looking at contamination present in these filter aids, you can see that again cellulose has lowest contamination. Again, if you are interested in the particle size, then you see a large variation in the particle size, and the permeability values also changes quite a lot, starting from very low values of permeability going up to almost a factor of 1000. The most important property, as we remember in the Darcy's law, is the specific cake resistance of the cake or permeability of the cake. Okay. So the permeability is inverse to the specific cake resistance. So we talked about different types of models. In the first model, when we assume that the filter medium does not offer resistance, we just had the properties of the cake, that means specific cake resistance, and then later looked at a model where we said the filter medium also offers some resistance. Now in the third situation, you may have a situation where the filter aid or pre-coat also can offer some resistance to the flow of the liquid. So the velocity of the flow of the liquid is equal to 1 by area of the filtration multiplied by the volume that needs to be filtered and the time. So this gives you the rate of filtration, this gives you the velocity, and here you have the area. Now this is related to the pressure, that is the pressure you are applying, viscosity of the fluid, and various resistances. There are 3 resistances now. So there is resistance offered by the cake, number 1. There is a resistance offered by your pre-coat or the filter aid, and the resistance offered by the medium, that means filter cloth or stainless steel filter or ceramic filter. So all these 3 may be offering resistance at various degrees, so you need to keep that in mind. So cake may be offering the maximum resistance, and then you may have the filter medium offering resistance, and finally the pre-coat may be offering resistance. So if you know all these values, we can introduce all these here, and then we can integrate these equation and calculate the time required for filtering certain volume of slurry, just like we did in the previous cases, if you recall all those actually. Another technique by which we can remove some of the solids present in your slurry which prevents your filtration process is by adsorption. Sometimes, as I said, the filter aid itself does this adsorption process. That means some of the unwanted material can get adsorbed on filter aid. After all, we are adding a pre-treated or processed clay or cellulosic material or wood chips or carbon and so on. So they have certain surface area which can aid in the adsorption of some unwanted material. So adsorption is another approach by which we can improve the filtration process. So there are two phases in any adsorption process. We have it is a multi-phase process. You have the fluid containing your solute and other contaminants, that is fluid means the slurry, and then the adsorbent, that is the porous solid which selectively adsorbs a contaminant or a solute. Okay. So what happens is during this process of adsorption, the components from the liquid gets transferred and gets attached to the adsorbent or the porous solids. So there is something called a mass transfer and there is something called the equilibrium. So the adsorbent cannot adsorb all the solute and the adsorption process depends upon the equilibrium concentration. So each solid has certain capacity beyond which it cannot adsorb the contaminant or the solute, number 1, and number 2, the mass transfer determines the rate of adsorption. So the mass transfer determines how fast or how slow the adsorption process is, and the equilibrium concentration determines how much I can adsorb. So depending upon the concentration of solute in my slurry and how much of solute I want to remove from the slurry before I resort to filtration, I will decide on the quantity of the adsorbent, understand, and depending upon the mass transfer I will determine how long I will perform the adsorption process. So depending upon the mass transfer, if the mass transfer is very fast, I will perform the adsorption very fast. If the mass transfer rate is very slow, the adsorption also will be very slow. So I need to give sufficient time for the solute to get adsorbed, and depending upon the equilibrium concentration I will decide how much of solid I need to add into the slurry. So the mass transfer and the equilibrium determines the thermodynamics and the kinetics of the process. Mass transfer determines the kinetics, equilibrium determines the thermodynamics, understand. So adsorption is a very selective process. We will talk about adsorption later on in more detail. We will look at different types of adsorption processes, we will do some problems on absorption, but as you know, adsorption can be very selective. Only the desired product can be adsorbed directly from the broth, fermentation broth. We do not need to do preliminary filtration. So we can do adsorption and then we can do the preliminary, and it generally does not denature sensitive biomolecules. So it can be preferable for proteins actually. So generally it does not denature the biomolecule. So we can have particles or solids adsorbents, it can have various sizes, it can be very small particle going right up to very large particle as well actually. So we can use activated carbon from vegetable origin, we can use clay, minerals, we can use natural and synthetic zeolites. Zeolites are nothing but different types of alumina. We can use molecular sieves, we can use normal alumina, gamma alumina, alpha alumina, we can use silica gel, we can use ion exchange resin, different types of ion exchange resins, cationic resins, anionic resins, they are all attached to polymers like styrene or cross linked divinyl benzene polymer. So a large number of adsorbents can be thought of varying particle size depending upon what you want to adsorb from the slurry. As I explained before in the previous slide, the quantity of adsorbent you would like to select as well as how long you want to do the adsorption process depends upon the thermodynamics of the process as well as the kinetics of the process. That means equilibrium concentration of the solute or the partition of the solute from the liquid to the solid as well as the mass transfer rate. So these are the two terms which come into deciding on the absorption process. Another approach by which we could improve the filterability is pH adjustment. Sometimes when you change the pH, some solids will precipitate out, solids which looks like flocks will agglomerate and then start precipitating out. Once it precipitates out, filtration may be very facile. Sometimes you like to denature proteins so that once it gets denatured it can precipitate out. So by altering the pH of the medium you can improve this type of process actually. So we can add acetic acids in the pH range of 4.5 going right up to 8.5, okay, and we can add lactic acid up to a pH of 3.5. We can use diethanolamine especially in the alkaline pH. We can add sodium carbonate up to pH of 10.5, sodium or potassium hydroxide going up to very large pH 11. We can add phosphoric or sulfuric acid at pH 2 to 3. So you see that if I want to move into acidic range or if I want to move into alkaline range, I can consider all these acids and alkalis depending upon the denaturization of the protein and precipitation of the protein, we can select the pH. So once we denature a material then we allow it to precipitate and settle down, we need to put in some time so that it settles down completely to the bottom of your vessel. So pH adjustment is also a technique, but then you need to decide on how much of this acid or alkali you need to add, how much of sodium carbonate I need to add, or how much of phosphoric or sulfuric acid I need to add, so that the unwanted material precipitates out. Now let us look at the filter media. Filter media is also part of your filtration setup. So if you look at this particular filtration assembly, you assume this as the cake or the solids which settles down, and this as the liquid which is getting the slurry, and the liquid the clear liquid comes down here. This is called the filter medium. This sort of supports your bed of solids and it has certain particle size. So depending upon the particle size of this filter medium we will be able to filter different types of slurry. So this can be made of different materials, polymeric materials, membrane materials, ceramic materials, stainless steel, cloth and so on, depending upon the process which you are studying, and each material has its cost associated with it as well as advantages and disadvantages associated with it. So commonly used filter medium, filter paper, we use it in our lab. So then after the filtration we throw the paper out, we sometimes burn the paper out to collect the solids and weigh the solids and find out how much solids is present. Woven material, cloth, different types of cloth, nylon cloth, polyester cloth, cotton cloth, cheesecloth, woven polymer fiber, woven glass fibers, non-woven fiber pads. That means you can have thick pads like in car we have, or air conditioners for example, we have pads which capture very fine particles and holds it. Sintered and perforated glass, sintered and perforated metals, if the solids are going to be abrasive it is better to use a metal type of filter medium. Ceramics, if you are talking about high temperature filtration, ceramics will be able to withstand these high temperatures. Membranes, synthetic membranes, different types of membranes, hydrophilic membranes, hydrophobic membranes. So all these materials are being used currently. Some of them are very inert, they can withstand very high temperature, they can take in abrasive materials, they are long lasting, some of them are short lasting, so you need to replace these filter media. So the cost of your filtration, the working capital I would say, depends on how many times in a year or month you replace this filter medium. So look at the porosities of these filter medium. It varies from almost 5 writing going up to 85% free area available actually. So we are talking about wire screens, woven wire, perforated metal sheets, porous plastics, sintered metal, Kieselguhr, membranes, paper, metal fibers, ceramics, foams, plastics. So large number of synthetic or natural materials are used for this filtration process actually. So they can be grouped into solid fabrication, metal sheets, rigid porous media. This is based upon the rigidity of this filter media. They also act as a support for the bed that is getting accumulated over a period of time during the filtration process. So they should have sufficient mechanical strength, and the smallest particles they can capture also varies. You can see that very small particle less than a micron going right up to hundreds of microns. Ceramics, sintered metals, powders, carbons and so on. We can have wires, mesh material, and then we can also have discs. Okay. So we have solid materials, metal sheets or rigid porous material. Going further, cartridges, we have different types of cartridges. We can have ceramic material, we can have solid metal, then we can have plastic sheets, we can have membranes. Again membranes, you can have polymeric membranes, metal, ceramics. When you talk about membranes, the particle size that can be filtered becomes very small. We can go down to very small 0.1 micron or even less than 0.1 micron material can be. Then if you look at woven media like fiber yarns, polymeric fiber yarns, they can capture only about 5 micron sized particles. Then non-woven material like papers or sheets, then loose media like fibers and powders. So large number of different morphology, different structures, different types of preparative method can be thought of depending upon the type of application you are looking at, depending upon the thermal conditions, depending upon the pH conditions, depending upon the percentage of solids that needs to be retained, depending upon the properties of the solids one can select. So two types of filter media we can think of. One is called the surface media. This is the normal filtration where a solid sieve, it traps the solid particles. They are used in a surface filter. Then you have depth filters where the particulates are captured within a porous body. So the depth filter will have a several layers of material which captures the solid which you need to filter. So surface filters can be Buchner funnel, which we use it in our lab, belt filters, rotary vacuum drum filter, we looked at it in detail some time back, then crossflow filters, screen filters and so on actually. The other approach is the depth filter. So you have a bed, granular material bed of varying particle sizes, granules, pebbles, sands, which try to capture the solids present in a fluid. Especially this type of depth filter is used in water treatment facility. They are also called as sand filters. This first type allows the solid particles, that is the residue, to be collected intact, and the second, this type of depth filter does not allow you to collect the solids back, whereas your the surface filter allows you to collect the solids intact, whereas the depth filter does not allow you to collect the solids intact. So here we are more interested in the liquids, and the amount of solids that is present is not also very large. So in that situation depth filter is ideal. whereas if you are interested in the solids, or if the amount of solids present in your slurry is very large, surface filter or belt filter is the best approach. There is one way of doing filtration apart from the normal way which all you know. This is called the dead end filtration. That means you add your slurry, you have the filter medium here, you have the cake getting slowly deposited, you have the slurry, the liquid starts flowing through these various resistances depending upon the pressure you apply. This is the normal approach. There is another approach which is called cross flow filtration. That means the slurry comes in a cross fashion and the liquid is, majority of the slurry comes in this cross fashion. Okay. So the feed travels tangentially across the surface of the filter setup. So what are the advantages of this? As you can see, in the normal approach your bed is sitting on top of the filter medium, so it slowly blocks the holes and your filtration process stops. Whereas in the cross flow, because the liquid is flowing like this, it sort of washes the solids that is settling on top of the filter medium. So it prevents the clogging of the solids, so it really prevents the solid clogging actually. So in a normal dead end filtration, after some time you need to remove the solids, that means it is a batch process, whereas in a cross flow filtration we can do it in a continuous process actually. So that way I can prolong the filtration time. So that is the main advantages with the cross flow filtration. But there is one disadvantage in the cross flow filtration, that is when the liquid is or the slurry is moving across or tangential to the filter medium, it sort of rubs the filter medium. So if you have a polymeric membrane as your filter medium, the polymer gets slowly eroded because of the liquid slurry flow which is tangential. So that is the main disadvantage of this cross flow filtration. Otherwise it has got quite a lot of advantages when compared to the normal dead end approach actually. So the membranes can be polymeric or ceramic in a cross flow filtration. So this is generally used in reverse osmosis or nanofiltration, ultrafiltration, microfiltration and so on. We will talk about all these in a membrane based processes later during the course of our work. It is also used in protein purification, this type of approach actually. So we can use it at different stages of the membranes process, and we can use cross flow filtration for different types of membranes also. So advantages, as I said, removal rate is very good and it prevents the cake formation, and the feed remains as a mobile slurry, unlike a normal filtration where you have the solids and the slurry sitting on the solids. We can look at different percentages of solid present in the slurry, and it can also do fractionation of the particles by size. That means I can get solids of different sizes separated using this type of approach actually. If you look at Buchner funnel which we use in our lab, we can do the filtration process by the suction. So here you have the filtration medium is generally a filter paper. So this approach is very good, it is a quick process, it is simple. So the solvent gets drained at the bottom and it happens because of the force of gravity. Generally it is used in laboratory applications. Belt filtration is another approach by which solids can be separated out in a continuous fashion from a liquid, and here we are more interested in the solids, not on the liquid. This is very good for paste type of material where you are wanting to remove just the water or solvent present in the paste. So this is called dewatering. So what you have is, here you have a belts, two belts generally made up of filter cloth or porous cloth, and these belts travel between these rollers, rotating rollers. So your feed slurry comes in and these belts move in this direction, and when they go through these rollers, the wet feed gets compressed, so the liquid gets sort of squeezed out, and at the end of it you have dry solids falling out. So again the belt moves back, and here again you are feeding your wet solids. So as it moves, the two rollers compress your solids, so the water gets squeezed out and here you get dry solids. So this is the advantage of it, and it is useful for dewatering of wet paste and soft paste and compressible paste. So here we can either have a scraping unit, or if the solids are not getting compressed, it can fall out on this side. So belt filter is used as a continuous process, because here continuously slurry can be fed in, and then continuously you can get the dry solids, and then the dry solids can be fed into a continuous oven or a hot air dryer, and it can be dried still further. So it is used in fertilizer industry. So the effectiveness of the operation can be increased by creating pressure difference across the filter cloth. That means you can bring in the filter rotating drums closer, or the rotating drums can be kept further. So the closeness of the rotating drums determine the pressure that is applied to the wet paste. I talked about depth filter, and this is a typical depth filter. A sand filter is a typical depth filter which is used for purifying running water. It is used in water treatment facilities, it is used in rainwater harvesting and so on. So in the depth filter what you have is, you have layers of particles of sand here, big aggregates here, pebbles here. So as the rainwater flows through, the solids are captured at different places and the filtered rainwater flows through. So you see this is useful only if you are not interested in collecting the solids, whereas you are more interested in the liquid, number 1. Number 2, the amount of solids present is minimal, because if the amount of solids present is very large, then it will block over a period of time, it will block the entire filtration assembly, because here you are not going to collect the solids, they will be captured at different places. Some solids, depending upon the particle size, may be trapped in the sand, some may be trapped in the pebble, some may be trapped in the aggregate. So these filters are useful generally for rainwater harvesting or water purification facilities. So how do they get captured? The direct collision between these particles or wasteful material with the sand or pebbles present. There could be van der Waals forces, there could be surface charge based attraction, there could be diffusion and so on. So different types of interactions take place as the fluid moves through this depth filter, and the solids in the fluid gets captured or removed. They are very useful and simple, very cheap, and once you set up this type of filtration assembly, it can last for many years. As long as the percentage of solids present in your slurry is minimal, these depth filters are extremely advantageous, and the operating cost is practically zero. You do not need to spend any money on chemicals or any money on utilities and services, and mostly they operate under gravity. So you are feeding the liquid or water from the top, and because of the gravity it flows down, and then it flows downstream into various locations or places or various points in the plant. So that is the main advantage of these depth filters. So the operating parameters for rapid pressure, so it can be operated at very low pressures, 2 to 5 bar maybe. Generally if the entire sand bed is very clean, the pressure drop also will be minimal actually, but over a period of time, if you are accumulating wasteful material, if there is going to be a biological growth taking place, then slowly you may find that the pressure drop across these increases. So those periods of time maybe you need to wash these type of sand filters. So they are, as I said, they are extremely useful for water treatment type of application. Then you have screen filters. These are screen filters you might have seen for filtering or separating large particles, large rigid particles of various sizes. So we can use a large screen, rigid screen, metal screens, or even polymeric like nylon based screens to separate sand or other fine particles. So these are again used in industrial applications. So the type of material you may use is stainless steel or iron mesh, polypropylene mesh, nylon mesh, polyester mesh. So they are very rigid, they are very rugged, they can last for a very long time. So you can have mesh of different sizes, that means different holes. So you will also be able to separate the particles into different categories depending upon the particle size. So these filters are very ubiquitous if you are interested in collecting particles of various sizes. Okay, so we have been covering a wide range of subjects relating to solid liquid separations over the past 4 lectures, and I also mentioned that this is almost the first, mostly this is the first step after the fermentation or a biotransformation, and here you are removing the solids from a fermentation broth. In some cases you may be interested in the solids, in some cases you are interested in the liquid. If your material or product is intracellular, you will be interested in the solid or the biomass. If you are interested in the metabolite, extracellular metabolites, you are not interested in the biomass or the cell debris, so you are interested in the liquid. If you have a material which is very suspended and it does not form precipitate, you may have to perform certain pre-treatment operations. The pre-treatment operation, wide ranging operations like increasing temperature or adjusting pH or adding certain flocculating or coagulating agent, or using an filter aid or an adsorbing material. So all these different approaches can be adopted to improve the filtration process. Once you have improved the process, you go into filtration. It can be like a depth filtration or it can be a surface filtration. So in a surface filtration, the bed starts accumulating, the bed of solids on top of a filter medium. The filter medium can be of any material, starting from metals to ceramics to polymeric material. The bed as it forms, it can be compacting bed or it can be compressible bed, which will slow down your filtration process. So you add a filter aid to that, so that the filtration is very facile. Then we developed an equation using Darcy's law, which will determine the time required to filter a certain amount of slurry. So the time we found out depends upon the permeability of the bed or certain properties of the bed material. It depends upon the pressure you are applying, it depends upon the viscosity, it depends upon the amount of solids present in the fluid. Sometimes you may have to resort to centrifugation, because in centrifugation you can resort to very high pressures. Then we looked at different types of centrifugation. We looked at something called tubular bowl centrifuge, we looked at something called the disc centrifuge. In the tubular bowl there is a bowl, and in disc you have many discs. So what happens during centrifugation operation, because of the centrifugal forces, the solids are directed to the walls, and the main equation can be very simplified into the throughput through a centrifuge is directly proportional to the terminal settling velocity of the solids multiplied by certain parameters which determines the centrifuge properties as well as the operating conditions of the centrifuge, right. So the centrifuge properties and operating conditions of the centrifuge we can get it from the vendor. The terminal settling velocity of the solid depends upon the physical properties of the solid as well as the fluid which you are using, which you can determine from your lab. So we can use this equation for scaling up when we move from very small scale right up to a very large scale. Then we looked at something called the centrifugal filter, that is the walls of the centrifuge are porous, so the solids start accumulating at the wall. So you form, instead of a flat bed of solids, you will form something called a cylindrical bed of solids, and the liquid comes out from the circumference. And then we looked at the equations related to the centrifugal filter and compared it with the normal flat bed filter. Then finally we looked at the scaling up operation. Scaling up when I move from a flat bed filter to a centrifuge, or when I move from a small centrifuge to a large centrifuge, because ultimately whatever data I collect in my lab I make use of it to perform a scale up, which will help me to design a centrifuge or filter which can process a large amount of slurry. So I went into that particular set of calculations, and also we looked at a large set of problems which tried to address these various aspects of filtration. So the main equation that comes into filtration, as you can see, is the Stokes law, which determines the settling time or the terminal settling velocity, and the Darcy's law, which tells you the relationship between the quantity of liquid or slurry that needs to be filtered as a function of several parameters like pressure drop, physicochemical properties of the liquid, as well as the ease of filtration. Okay.